Now we continue. Now we continue our readings with lectures of Georgy Ryabov, singular stochastic differential equations and stochastic flows. Please, Georgy.
Okay, thank you for the introduction. I have two lectures. During them, I would like to present a theory of stochastic flows as it is developed by now, and also give some applications to stochastic differential equations with singular coefficients. Today, I will speak mostly about general stochastic flows. And let me start with some well-known examples. So let us consider a stochastic differential equation with the smooth coefficients. The equation 1, here we have coefficients A and B. A is a drift and B is a diffusion, and I assume that both are continuously differentiable and bounded. Of course, in this case, such equation has a unique strong solution. And moreover, this equation can be solved simultaneously for all starting times s and all starting times x. It means that one can find a family psi stx that solves the equation, okay, for fixed s and x for all t. Since there is a unique strong solution, we immediately have the so-called weak evolutionary property. It means that if we start from psi rsx, then we will almost surely coincide with psi rtx for all t greater than s. In fact, one can do more, and one can show that there is a modification of the process psi, which I also denote by psi, such that the evolutionary property holds almost surely for all RST. So there is some exceptional set of measure 0, and outside which the composition of two mappings psi rs and psi st equals to psi rt. Also, each mapping psi st is a random homeomorphism of the phase space. On disjoint intervals, random mappings psi act independently, and they are stationary in the sense that the distribution of psi depends only on the difference t minus s. And also in this case, the modification can be made continuous in st and x. So this is a good reference where it can be found, this result. And if we look at the last three properties, we can say that psi, in a sense, is a Brownian motion, but it is a Brownian motion in the group of homeomorphisms of RD. However, there are interesting flows that are not consist of random homeomorphisms of the phase space. And as an example, let us look at the Ryabov flow, which I think was already discussed here. So there exists a family of random mappings of the real line UST with the following properties. So if we fix S and X, then we get a Brownian motion, and these are Brownian motions with respect to the same filtration, and their quadratic variation equals to t minus tau, okay, max 0. It means that the increment of the quadratic variation is equal to 1 when t is greater than the meeting time, and it is equal to 0 when t is less than meeting time of two trajectories of the flow. As a consequence, before meeting trajectories move independently, and after meeting they coalesce and move as a one. And also it is a stochastic flow in the sense that the composition of mappings URS and UST is equal to URT, and they act independently on the disjoint intervals. On this picture, on the left picture, we see a realization of three trajectories from the Ryabov flow. So here, two of them started at time s, and they have coalesced before time t. And then there is one more that started at time t. If we look at realization of one random mapping from the Ryabov flow, it looks like it is actually a random step function. So, of course, it is not a homeomorphism of the real line. And actually, its behavior at moments of jumps is quite interesting, but I will not speak about it too much today. So this flow appeared naturally in a number of works. Initially, it was discovered by Aratia when he started a voter model on integers. Later, Tsirelson used it as an example of the flow that produces a black noise. Again, it was used to construct a so-called true self-repelling motion. So the Brownian web is a different way to look at the Ryabov flow. It is a closure of the family of all the trajectories of the Ryabov flow in the Hausdorff distance. Also, Ryabov flow appears as a weak limit of some stochastic differential equations with interaction. And recently, it was also found to be a limiting object in the model of diffusion limited aggregation and oriented percolation. Since it is a flow of coalescing Brownian motions that are independent before meeting, it is it is not a flow of solutions to some stochastic differential equation. In fact, if we want to write a stochastic differential equation for a Ryabov flow, it should look like this. So here we have uncountably many independent Brownian motions that start from all moments of time, from all points in space, and the increment of u when it is at some point y, it follows the increment of wty. But of course, this SD makes no sense. So, since there are interesting stochastic flows that are not produced by stochastic differential equations, we need a notion of a general stochastic flow. So this is the definition. Here, I will work in a locally compact separable metric space equipped with a Borel sigma field. We saw that as functions of the phase, the state variable, we may not have smooth functions. So I will assume that random mappings from a stochastic flow are just measurable in a state variable. So F is the space of all measurable mappings of M, and it can be equipped with the cylindrical sigma field. Now, by a stochastic flow, I will understand a family of random elements in F, meaning that it is a family of random measurable mappings of the phase space, such that we have the flow property. This is the first one. On disjoint intervals, mappings are independent. They are stationary in the sense that the distribution of psi st depends only on t minus s. And also, I will assume two more properties. These are the last two. Actually, these are like weak continuity properties, and they are needed for trajectories from the flow to be Markov processes good enough, in the sense that we will see from these two properties that trajectories of a stochastic flow are actually failure processes. So point number 4 is continuity in time, and property number 5 is a continuity in state variable, and also if f converges to 0 at infinity, then this expectation also converges to 0 at infinity. So this looks like a reasonable definition of a stochastic flow. However, there is a problem with this definition. It turns out that modification of a stochastic flow may not be a stochastic flow. So let me show you an example. As a probability space, I consider just the unit square with the back measure, and as a phase space, I consider just a segment. And I will not construct like the full flow. I will construct only the flow between 0, 1 and 1, 2. So psi 0, 1 is omega 1. It sends all points into omega 1, as well as psi 0, 2. Psi 1, 2 is omega 2 if x is not omega 1, and omega 1 is x if x is omega 1, and psi 1, 2 tilde is always omega 1. I will change only psi 1, 2, and of course psi tilde 1, 2 is a modification of psi 1, 2, because they are equal when the first component of omega is not equal to x, and this happens with the probability 1. Now, psi is a stochastic flow. Yes, in fact, it is even a strong flow. But if I change psi 1, 2 to psi 1, 2 tilde, it satisfies evolutionary property with probability 0. Indeed, psi 0, 1x is omega 1, and psi 0, 2 is also omega 1, but psi 1, 2 tilde is always omega 2. So they are never equal. An explanation for this problem is that if we consider the evaluation mapping on the space of measurable functions, then it is not measurable. So we cannot apply Fubini theorem. Now, I will give a definition that allows to fix this problem. So a probability measure Q on the space of measurable mappings is called regular if if the evaluation mapping has a measurable modification. It means that there exists a measurable mapping I from a mapping F and point X, such that for every fixed X, almost surely I phi X equals to phi X. This mapping is called the measurable presentation of Q. And actually, it is quite a subtle property. So if the distribution is regular, then the corresponding process, if we look at it as a process on M, has a measurable modification. Up to now, it is not known whether the converse is true. And I think it is not true because there is a related example in this work. Actually, in this example, Dudley constructed a measurable process such that the evaluation mapping is not measurable with respect to the product of distributions of this process and time. As I know, it is still an open question, but it seems that there are measurable processes whose distributions are not irregular. Okay, so now having this definition, we can define the proper definition of a stochastic flow. Again, psi is a family of random elements in F. Qt is the distribution of psi 0t. And actually, this is the same definition as it was before, but property 2 changed a little bit. So property 2 now means that for all moments STU and all points X, and all measurable presentations of the distribution of psi ut, we have the evolutionary property. However, now we need to substitute not psi st into psi ut, but we need to substitute it via the measurable presentation I. And well, this definition appeared like 2020. Okay, so with the new definition, we don't have the problems with the modification. If psi prime is a modification in the sense that psi prime is equal to psi almost surely for all st and x, then psi prime is also a stochastic flow. Indeed, since psi prime is a modification of psi, the distribution of psi prime is qt minus s. And now let us consider the mapping theta that maps three functions phi into the following. So the first component is a composition of phi2 and phi1 via measurable presentation I, and the second component is phi3 of x. And now this mapping is measurable. So if we consider the probability that psi prime is equal to the composition of psi prime ut and psi prime su, it is the same as the triple belongs to the pre-image of the diagonal under the mapping theta. Now the mapping is measurable, so we can consider this event. And since psi prime is a modification of psi, it is equal to the same probability for psi. But psi is a stochastic flow, so this probability is equal to 1. Okay. Now I will discuss two ways to describe stochastic flows. Assume that we have two distributions on space of measurable mappings, and assume that Q1 is regular and I is its measurable presentation. By the convolution of Q1 and Q2, I will understand the distribution of the convolution of phi1 and phi2. Yes, so this is this is a composition of phi1 and phi2, but we use it via the measurable presentation I. So Q1 and Q2 are independent, and we compose them using measurable presentation I. What we get is again a measurable mapping on M, and its distribution I will denote by Q1 convolution Q2. Now, the distribution of the convolution is independent from the choice of I, because again we can use Fubini theorem, and when we fix Y, then I of phi1y and I prime of phi1y are almost surely equal. So this is a correct definition of convolution. And the next notion is the notion of Feller convolution semigroups. We have a family of regular probability measures on space of mappings. We will say that it is a Feller convolution semigroup if the convolution of Qt and Qs is equal to Qt plus S. And last and second and third property, they resemble the usual properties of Feller transition functions. So when T converges to 0, we have a uniform convergence in L2 sense, and we have a continuity in state variable, and also we have a convergence to 0 when state variable goes to infinity. Now, from every stochastic flow, we can get a Feller convolution semigroup. So let psi be a stochastic flow, and Qt, it is the distribution of psi 0t. Actually, then we can show that it is a Feller convolution semigroup of regular probability measures. Let us recall that the regularity of distributions is by assumption. To check that the convolution of Qt and Qs equals Qt plus S, we just write it by definition, and here we can substitute for phi1, we substitute psi S plus T, and for phi2 we substitute psi 0s, because they are independent with the proper distributions. And then we use the flow property and get that Qt is a convolution semigroup. And actually, second and third property, they are the immediate consequences of continuity of the flow. Second is continuity in time, and third is continuity in space variable, and also converges to 0 when space variable goes to infinity. The next definition that I need is the notion of the notion of endpoint motions of the flow. Let us fix n dimensional point in the state space. So x1, xn belongs to M, and by Pn txb, I denote the distribution of the action of the flow on this point x1, xn during time t. Okay, so actually P and T, it is the distribution of n trajectories from the flow. Then it holds that for each n, Pn is a transition function on m to the power n. Every transition function must be measurable in x, and now it holds since Qt is irregular. So actually P and T, it is the measure Qt of such mappings phi that phi x1, phi xn belongs to B, but we can replace phi with its measurable presentation, and then it is clear that it is measurable in x. And the Chapman-Kolmogorov equation is also easy to check, because we have Pn. Pn is finite dimensional distribution of the convolution semigroup Qt. Okay, so this simple calculations show that each Pn is a transition function on the phase space to the power n. In fact, it will be a Feller transition function. So let me give it a proper definition. Okay, so for each n, we have a transition function on m to the power n. We will say that Pn is a sequence of coalescing Feller transition functions if each Pn is Feller. Second property is a coalescing property. So if we have two processes that started from the same point, then they always must be equal. Okay, and the last property is a consistency property. So if we have Pn, it is the distribution of n trajectories, and if we sample k trajectories from them, then we will get actually the motion of these k trajectories. Okay, and then to every Feller convolution semigroup, if we define Pn as above, then actually it is a sequence of coalescing Feller transition functions. So to check the Feller property, it is enough to consider functions of the following form. So assume that f is the product of functions of one variable x, and these functions are continuous and vanish at infinity. Then we can estimate the difference p and tf at point x and at point y as follows. So first I write it by definition as integrals over distribution Qt. Then I can add and subtract the products for x and products for y for some k and get the following inequality. So now, okay, all j are bounded, and we have the Feller property of Qt, which implies that we have which implies that P and Tf actually is continuous. Similar computations show that P and Tf converges to 0. So these transition functions send C0 m to the power n into itself. And again, from properties of Qt, it is easy to show that P and Tf converges to f as t goes to 0. Every function from C0m to the power n, which is missing here, can be uniformly approximated by finite sums of such products. So it shows that the transition functions are Feller. Okay, now coalescing and consistency properties are quite easy because P2 is the probability that a random mapping phi sends, okay, phi x, and phi x is equal to phi x, yes, but of course it is always true, so it is equal to 1. And consistency also follows from the fact that actually P and T is a finite dimensional distribution of Qt. Now, what we have done, we defined a stochastic flow. From this stochastic flow, we constructed a Feller convolution semigroup, and from every Feller convolution semigroup, we constructed a coalescing Feller transition functions. And what we will do next, we will try to go back. So from coalescing Feller transition functions, we will construct a Feller convolution semigroup, and then we will construct a stochastic flow. Uh, the material that I'm talking about today mainly follows the work of Lejean and Raymond, but with some exceptions, because I introduced some new approaches to their work. Actually, there will be two of them, and we will need them later. Okay, so their theorem states that when we have a sequence of coalescing failure transition functions, then one can construct a failure convolution semigroup whose finite dimensional distributions are given by Pn. So as a warm-up, let us consider the case when M is finite. Okay, this is the easy case. We enumerate all points of M and simply define Qt as the distribution under Qt, the values phi x1, phi xd are distributed as ptd of x. Now, in the finite case, all measures are regular, and what must be checked is that the equality for Qt holds not only for x1, xd, but actually for all points z1, zn. Maybe some of them are equal, and for all y1, yn. I separate z into subsets where they're equal, and it is enough to consider the case when for each non-empty ik, all values y are equal. Because if they're not equal, we have a coalescing property of P2, which will say that the probability P is equal to 0 and the probability Q is also will be equal to 0. Okay, so then we can write this probability as follows. And here, so we get the probability that phi x1, phi xd belongs to the pre-image under pi of these values. And here we use consistency of P. And on the other hand, when we consider P and T, we also can use the consistency of Pn. So this proves that probabilities Qt satisfies this property. Okay. Now, from this, it is easy to check that Qt is a convolution semigroup, and actually, the Feller property now easily follows from the Feller property of P. Indeed, let us consider a continuous function that vanishes at infinity and compute the integral of f of phi minus f squared under the probability Qt. We just open the square and note that the first integral is P1 applied to f squared, the second is minus 2f P1f, and the third is plus f squared. And now this converges to 0 uniformly. It is clear, yes, because we just have f squared minus 2f squared plus f squared in the limit. And to check the continuity in the state variable, again, we open the square, and when y converges to x, we get 2 pi 1 applied to f square minus 2 pi 2 applied to the product ff, yes, of the point xx. But since we have a coalescing property, P2 applied to the 10⁻⁴ of f is equal to P1 applied to f squared. So we get what we want. It is a Feller convolution semigroup. When M is infinite, we still can construct Qt because we have its finite dimensional distributions. But it is not clear why it will be irregular. So I will show how to construct Qt already to be in the construction, it will be clear that it is a regular distribution. For this, I will prove first lemma 1. This is a lemma about a measurable selection of limit points. Actually, we will use this lemma later. So I prove it for any complete separable metric space. Lemma states that there is a measurable mapping L that sends any relatively compact sequence into its limit point. So mapping L in a measurable way chooses a limit point of relatively compact sequences. When the space is compact, this mapping can be constructed as follows. So just pick some dense sequence and okay, L0 is this sequence, and then we proceed in the following way. So assuming that Lm-1 is constructed, we define dm as the lim sup of distances to point Zm, choose a subsequence where this lim sup is achieved, and define Lm as L-1 over this subsequence. And then choosing a diagonal subsequence, we can show that the distance from this subsequence to every point Zm has a limit. Since the space is compact, it means that the point itself has a limit, and by construction, it will be a limit point of our initial sequence. Okay, and when X is not compact, since it is complete and separable, it is homeomorphic to some Borel subset of a compact space. As an example of this homeomorphism, we can choose, for example, distance from X to some dense sequence, minimum 1, okay, and consider this as an element of a compact space 0, 1 to the countable product of segments 0, 1. Okay, since F is a homeomorphism onto a Borel subset, it has a measurable left inverse, which I denote by G. Now, for the compact space, for the compact space X, we have already constructed the measurable selection mapping L, and I will define a measurable selection for X as the following. So first, to every having a sequence in X, I apply F to every element of the sequence. Then I apply the measurable selection L for the compact space, and then I apply the inverse. And then actually this L is what we need, because if the sequence X is relatively compact, okay, so L when I apply F to this sequence, L tilde is a limit point, so it is a limit of some subsequence. But since X is relatively compact, we can assume that it also converges in X. So the limit point of f of X is f of some limit point of X. Okay, and it means that we have this measurable selection mapping. And the next property that I will need is a consequence of the Feller property of transition semigroups. Actually, if F is a closed set, then PT xf is an upper continuous function. The proof is quite standard because if we consider a sequence tk that converges to t and sequence xk that converges to x, then all these values lie in some compact set. Okay, when S is bounded from above, from the Feller property, we can find a compact where all distributions PSY are concentrated, and then we just we can approximate the intersection K and F by some by continuous functions, and get actually upper semi-continuity of PTXF. Okay. Now we will apply this to a special closed set. Let us denote by d epsilon, the delta epsilon points that are at distance at most epsilon. Then it turns out that PT xy, the delta epsilon converges to 0 uniformly when t is bounded, and when xy belong to the same compact set, and the distance between them converges to 0. This actually can be deduced from lemma 2. So we assume that there is no such convergence, then find sequences Tn, Xn, Yn, where the probabilities are greater than some alpha. And we may assume that Tn converges to T, Xn, Yn converges to the same point X, because now Xn, Yn belongs to a compact, and distance between them goes to 0. Okay, and then we get a contradiction with the coalescing property of P2. Okay. Since the space M is locally compact and separable, we can write it as a union of compact sets, such that each set Lk is contained in the interior of Lk plus 1. And previous proposition implies that for some sequence epsilon that converges to 0, if t is less than k and xy are in Lk and the distance between them is less than 2 epsilon k, we have the following inequality. To find epsilon k, it is enough to apply this proposition with epsilon equal to 1 over 2 to the power k. Okay, now let us find a countable dense set in M. And here it is important that all Zn are different. So that's why I separate the infinite case from the case of finite M. For every point x, I choose indices nxk as follows. So nxk, it is the number of the first element Zn, which is at distance epsilon k to x, and define the following mappings. So the mapping I does the following. It takes a sequence of points in M and turns it into a measurable mapping F in the following way. So at every point Zn, the value of this mapping will be Yn. And all the rest is constructed by using this measurable selection map. Mapping G does, in some sense, the converse. So it computes values of phi at points Zn, and mappings phi n and psi n are just a convolution of I. Okay. It turns out that all these mappings are measurable. Actually, it is enough to show that I is measurable, and since measurable selection is a measurable mapping, it is enough to show that Y is measurable, but it is actually easy. Okay, and then by induction, all mappings phi n and psi n will be measurable. Also, J is measurable, and J is left inverse to I. Indeed, if the point X is equal, so the mapping J computes I of Y at point Zn. But if X is equal to Zn, then our approximating sequence simply will be equal to N for all large enough K. So it has a limit, and Y and mapping I chooses its limit point. Yes, so it will choose the limit, and we get that J of I is equal simply to Y. Okay, now consider the following proposition. Here, X is a random variable in M, Y is a random sequence in M, distribution of Y is equal to PT. It turns out that if we approximate X by our construction and substitute it into Y, we will get almost surely IY of X. So why it is so? Because by construction, the distance from X to its approximation is at most epsilon k. It means that the distance between two subsequent points of approximating points is at most 2 epsilon k. Also, if k is large enough, we can assume that t is less than k, and these approximating points belong to the compact Lk. So by our choice of epsilon, we get that the probability that approximating points are at distance at least 2 to the minus k is less than 2 to the minus k. Then it remains to compute a conditional expectation and conclude that this probability is at most 2 to the minus k. Then if X belongs to some compact, then the approximating sequence Y and xk actually has a limit. So this limit must coincide with the Iy of X, because Iy chooses a limit point of Y. Okay. And one more property that I will need is that if I have two independent sequences in M, and what xn converges to x in probability, then actually our mappings I of y converge to Iy of x in probability. The proof is the same as the proof of previous proposition, and we only need to know that since xn converges to x in probability, then distributions of all elements xn and x belong to the same compact K with the probability at least 1 minus alpha. Okay, and here are some estimations that allow to prove the convergence of I of y xn to I of y of x. The mapping I, as we defined it, was measurable, and now finally we construct Qt as the image of Pt under the mapping I.
Georgi, could you please once more repeat the proof of the previous lemma in the formulation? So y is any random element,
Yes.
and xn are also. So the
X is a random sequence and Y is a random sequence. And we assume that xn converges to X, substitute it into I, and prove that IYXN converges to IYX.
And is it possible to formulate this proposition as some general proposition? Just there is a function f of xy, and f satisfies some continuity properties in x. If xn converges to x and x and y are continuous and are independent, then f of yxn converges to fyx. Because I is not continuous, but
it is not continuous.
Yeah, it is not continuous.
No. Maybe, I don't know. So I is not continuous in X.
So please explain one more time what was really important in the proof. Something like losing theorem or some continuity on a compact of the full.
No, the most important in the proof is our choice of approximation. So we choose. Let me show it here. Okay, so for every point x, we choose approximating sequence such that, in some sense, it converges to x fast enough. Fast enough in the sense that when the distance between x and y is less than 2 epsilon k, then the distribution of the corresponding map between x and y will be not big. Yes, it will be greater than 2 minus k with a very small probability.
So this mapping, because this mapping I was constructed in such a way.
Yes. So here the idea is that we have to approximate every point. Like we have a good approximation of every point of the space. Okay. And we defined Qt as the image of Pt by mapping I, and it remains to check that Qt has the proper finite dimensional distributions. Okay, by definition, the left-hand side is such expectation, and again, so here we use proposition 7. So this expectation, we can write it as a limit of expectation of approximations. Here we can substitute expectation by our transition function and use its failure property, because again, every approximation z and x k converges to x. So what we have done up to now, to every coalescing sequence of failure transition functions, we constructed the corresponding failure convolution semigroups. Okay, I didn't say why it is a convolution semigroup. Actually, this is it follows from the definition. What is interesting that the composition I and J, actually, it is a measurable presentation of Q. Because J composition I is the identity mapping. So here in this construction, every probability Qt has the same measurable presentation. And one more fact that I will need later is that actually, if we take independent sequences T1, Tn and apply the composition of I to these sequences, we will get Q of T1 plus Tn. So this is a fact that I will need next time. So in the next lecture, I will show that from the failure convolution semigroup, we can construct a stochastic flow. However, it will be a weak stochastic flow in the sense that evolutionary property holds almost surely for fixed S, T, U, and X. And one of the questions will be, can we improve it to be a strong flow, in the sense that almost surely we have a flow property. And also we will consider some stochastic differential equations with singular coefficients and construct stochastic flows of solutions to these SDEs, and we will see that they can be a stochastic flows of non-homeomorphic mappings. So this is all what I wanted to say today. Thank you for the attention.
Okay, thank you very much. Maybe somebody have questions or comments, please. If there are no questions, let me ask you the following. The problem of constructing of stochastic flows is rather old, and maybe the one of the first was who paid attention to this problem was Darling. And can you compare what you did in this lecture with his book, Construction of Non-Homeomorphic Stochastic Flows?
Yes, he actually showed that when you, let me go here, okay, to the definition, he even didn't have a failure property of transition functions. Mm-hmm. So he had only a sequence of coalescing consistent transition functions. And he showed that it is possible to construct as a flow, a stochastic flow, even a strong flow. So yeah, but he didn't have a measurability of this flow even in X.
Mhm.
So it is quite strange because you substitute one mapping into another. Yes, he got that if he substitute psi st into psi ut, he always get psi su, but you cannot substitute anything else into psi except for psi.
Mhm. Mhm.
And also, of course, he had no regularity in time.
Mhm. I remember that he has some special definition of convolution of two measures in the space of mappings.
Yeah, essentially, this is it.
Mhm. Mhm.
Yes, essentially.
Yeah. Okay. I see. I see. So can we say that the aim is to get the random dynamical system maybe consistent from non-continuous mappings?
Yes, yes.
Mhm, mhm. And the one of the proposals is to get some usual or regular properties for good dynamical system in this case.
Yes. So of course, when we define a stochastic flow, a natural question is how good modification we can find for it.
Actually, usually when we study random dynamical system, we want to look on the limiting behavior in the infinity.
Yes, yes.
So maybe the good properties of the flow mappings with respect to spatial variables can lead to good properties, good limiting properties. So if we have only measurable mappings, then we cannot expect everything from the good theory. Yeah.
Yes, of course. Yes.
Mhm. Okay. See what happens next time. Now, thank you very much, and we will continue with your lectures after a week. Thanks, everybody, and bye.